Okay, please.
Okay. I hope you can hear me now.
Yes,
Yes, we can.
Fine.
Yes.
So this is the first part of hopefully a short series of talks about the general subject of embeddings and predictability of dynamical systems. Today I will be speaking about so-called probabilistic Takens delay-embedding theorem, and generally it seems it does not work. Maybe I will be using. Okay. This is a joint work with Yonatan Gutman from IMPAN and Adam Śpiewak, currently at the Ilan University, and next year, hopefully here also. So I hope my co-authors will continue this series, maybe in the new year. We'll see. Okay, so the subject is very classical, dealing with quite general notions in dynamical system and also outside dynamical system in some embeddings in topology, geometry, and such things. So I would like to start with reminding some classical results about embeddings, not in the dynamical context, but just in topological and smooth categories. So the first result is well-known Menger-Nebelin theorem from the 30s about embeddings of compact metric spaces into Euclidean space. So it asserts that if you have such a compact metric space X of dimension D, of topological dimension D, so you can say Lebesgue covering dimension D, then if we take an arbitrary map from X into Euclidean space of sufficiently high dimension, exactly 2D plus 1 is enough, then a typical map in the topological sense, that is in C0 topology, typical means that it contains a countable intersection of open dense set. Typical transformation will be a topological embedding. Here, topological embedding is just a homomorphism. Okay. And the second result is also classical by Whitney about smooth manifolds. And it says that CR of dimension D can be embedded by a CR map into Euclidean space of dimension 2D plus 1. In fact, also a generic smooth transformation into this space is an injected.
Can R be omega real analytical? I think we use the Riemann structure.
Okay, so it is known that this embedding, minimal embedding dimension, which is 2D+1, is optimal in the sense that there are classical examples of, for instance, space compact topological metric space of dimension D, which cannot be embedded in R2D. Okay, so this is
2D is enough if you make big one. But this is different.
okay. So this is a non-dynamical set. Okay, and well, generally one can ask why these embedding theorems are important. Generally, an embedding is very useful because, for instance, in this setup, we have some abstractly defined object like manifold, and if we know that we can embed it in a nice space, Euclidean space, then we have some additional accompanying external structure, which allows us to well get a better description of this object. For instance, for smooth manifolds, we need not to define tangent space in an abstract way. We have just tangent space in Euclidean space and so on. Okay, so now general reflection on the approach to dynamical system by a theoretic mathematics and experimental science. So, what is a dynamical system for a mathematician? For a mathematician, this is just defined as a pair of a space and some semi-group of transformation acting on the space. So we just start with a notion of the space and the map. We just have this object defined at the very beginning to deal with it. But for people which do experiments, they think a bit in another way. So they know that there is some system which changes in time, which generates some dynamics, but they do not have a priori, they do not have a definition, a formula for this map. Even they usually don't know much about this phase space X. What they know are the just values of some measurable objects. So they have some observables, and observable here is just a function, a real function from the space, and they measure it. And they get something which they call time series, which is the sequence of measurements of this observable in time. So values of h of x, h of t of x, and so on. So that is what they start at. And then even if there is no dynamics, so one can say that any function from this space X to Euclidean space, so any function is a kind of function into Rk is a kind of a k measurements of independent, so maybe one measurement of k independent observables. Okay, so in this interpretation, this Menger, Nebeling, and Whitney theorems say that topological or smooth d-dimensional phase space can be reconstructed by 2D plus 1 independent measurement of independent generic observables. Okay. Now, if we have some dynamics and this time series, then this time series can be regarded as a sequence of measurements of one observable, but in many moments, different moments of time. And these are called time delay measurements. So generally we have this phase space. We have, well, either we have discrete map, or we can also have some continuous dynamical system, a flow, and then he just correspond to T1 or time one map, and the points in space undergo some evolution in time, and we have x, t of x, and so on. And after some times, there is a final moment, say this moment, and we measure this observable age. We have this measurement here, but also we can consider previous measurement. So we can consider age here, age here, and the first one is at time 0. So this is called the sequence of time delay measurements. But well, mathematically we just rather start from the time 0 and see the future. This is why it is called time delay measurements. So the question which we consider is, so suppose we have just one observable, but a long period of time, many measurements. Can we reconstruct the system just from measurements of this one observable, many measurements? So this is the question which was considered in the 80s.
You mean distinguish points?
Yes, well, yes. In the top of this English post, but just generally, philosophy is to get as much information as we can about the system. So this was studied by many people in the 80s, like Borel, Ekman, Takens, Ott, York, and many other people. And the main result, which I will be dealing with, is so-called Takens time delay embedding theorem from 1981. So to formalize, we take a beginning of this time series, a finite part of the time series for an observable age, up to time k minus 1, which makes exactly k terms, and we will call this k delay coordinate map. So the variable is x. We fix some large k and consider such a map. And Takens proved that if we have a compact smooth manifold of dimension d, then generically So for a generic pair of smooth diffeomorphisms on M and a smooth observable, this K delay coordinate map indeed will be an embedding, a smooth embedding into our K, as long as K will be at least 2D+1. So this is exactly like in the Whitney or Menger-Nebelin theorem. Okay. So in this experimentalist language, we can say that a smooth d-dimensional phase space with some generic smooth invertible dynamics can be reconstructed by 2D+1 time delay measurement of a general smooth observable. Okay, and this theorem became very famous in this world of experimental sciences. So this now it is a kind of a black box which is used for theoretic verification of some procedure modeling procedures.
This theorem follows from there's a general Thomas Mail transversality, which proves cosmate at the same time.
I don't know if it's
there is a proof of no Takens, because I think that the Takens didn't really give a full proof.
Because it is classical, it is called cosmate, which bases on May, the space of transformations. If you can do local something, then you can do it.
No, I don't think so.
It's what I didn't show you.
yeah, but of course the philosophy of the proofs are similar, but here you have this threshold 2D+1,
Right.
yeah, which is not present in general in Kupka-Smale. Yes.
Snail is do something locally and do it. And locally, if you have enough space to move transformation, this is what I remember.
Of course, this philosophy is like in the transversality.
Yeah, the transversality.
Yes, they use it. Yeah. Complexity, but an abstract. Infinite dimensions.
Okay. Okay, so indeed it is used in many contexts, in modeling some physical system, electronic, chemical reactions, or also some population dynamics, in biology, in modeling of epidemics. Okay. So formally, we see that the phase space can be embedded in the Euclidean space. But what is important in the dynamical context is that not only the phase space, the whole dynamical system can be embedded also in this Euclidean space. So just formally, if we have a homomorphism from X to the Euclidean, the subset of Euclidean space, then formally it gives conjugation of the dynamics of the dynamical system in this abstract phase space X to a subset to a system on the subset of Euclideans. Giving this map S, and this map S, it can be described such that S, so the value of pi is of the form h of x h p k minus 1 of x, And this S will be some shift here. H of T of X to H of DK.
Can you extend S nicely to neighborhood of variables?
Yeah, that is a question. Yes. So. Yeah, in this context of Takens theorems, so the space is compact. This so not only the phase space can be embedded, but also we have some reconstruction of the dynamics by this 2D+1 time delay measurements. Okay. So there have been many extensions or additions to this Takens theorem, which I call Takens type delay embedding theorem. So I will be talking about the first result mentioned here by Sauer, York, and Kasdali in 1991. This is a version for Lipschitz map. We will formulate it precisely. There is also some extension for non-autonomous dynamics. Also in infinite dimension space. So generally we have a Banach space, and so the maps are defined on some finite dimensional subset of the Banach space, but the space itself is dimensional. And for instance, if we have in the analysis of Navier-Stokes equation, we have sometimes finitely dimensional attractors, and they stick to this setup. So if you have some condition that this space are well approximable by finite. This is another Robinson. This is Robinson from Warwick. Yes. I think he's also James. I don't think.
I think he's James.
Yeah. Because the other one is Clark. Yes. Okay, he's James. Okay.
This Alto Clark, the one that you mentioned.
No.
Okay.
Okay. Okay. And there's also a topological version by Yonatan, valid for homomorphism of a compact metric space and continuous. Okay, so now I will say more about this Sauer, York, and Kasdali theorem, because we will be working in the same setup. So generally, they work in the category of Lipschitz map, and they consider genericity in some different sense, mainly in the sense of prevalence. So the notion of prevalence is, in a sense, well, this was the idea of introducing it, some analogous of Lebesgue almost sure condition for infinite dimensional space. So the notion is due to Hans, Sauer, and York from the 90s, and the definition is the following. So we have say a Banach space, or not necessarily Banach, just a complete linear vector space, V, and some Borel subset S in this space, and we say that it is prevalent, so it is big, if there is some Borel measure, nu, which is finite on some, here it is compact set, or in some variant of definition is a finite dimensional set of the space. And for every vector V in this big space, capital V, for almost every E in V, the sum V plus E is in S.
We can translate V by many ways.
So we take, so we have any vector V, and now we add vectors E. And for almost all vector E, we are in this set.
In this S.
S. Yes, in this big set. So this is a bit abstract definition, but we will use it in more concrete setup.
S can be taken.
So this is a quite interesting notion. For instance,
we know this notion from infinite spaces, but we know not in a bag what is finite dimensional functions.
yeah.
Your complex.
You can think about it like this. You have something, right? And now you want to perturb. And you want to, you have this set S in the background, which is big, right? You want it, but there is a compact set. So the first, exactly. So the measure controls in a way the directions where you can perturb. Right? So in that sense, it's big, but it's only big because you are perturbing the direction the measure gives you. So it's not all direction.
Okay, so for instance, in finite dimensional space, if you take Lebesgue measure, it's exactly the full Lebesgue measure. Okay.
So, excuse me, I have a question. So
Yes.
what are the conditions, other conditions on this Borel measure? Can it be just a point measure, a Dirac measure of a point?
Yes, but it is maybe it is not very interesting.
No, it says if there exists such a measure. The measure is not fixed.
I see, thank you.
Okay, so what we'll deal with some more concrete version of this definition, some sufficient condition. So generally, we will work in the space of Lipschitz maps. So this is on say on a compact space X, then a compact metric space X. Then this is a Banach space. We take some norm, Lipschitz norm here, and this variant of the definition of prevalence is the following. So we choose a finite set in this space, and it is called a probe set. So here we take M Lipschitz maps, and formally as this measure nu, we take Lebesgue measure on Rm. M is the number of this map, and we have a map psi which maps to any vector of coefficient. We take just a linear combination of
What
this.
was you read now? At the bottom?
Yes. Okay, so we take M Lipschitz maps, and we take a map psi. These are just points in Rm. Alpha 1, alpha m are real numbers, so this is a vector in Rm. So psi of this vector is just linear combination of them. Okay, and formally we take as nu, we take an image of the Lebesgue measure on Rm by this map. Okay, and then we say that prevalence with this measure is called prevalence with this probe set. Okay, and what does it mean? It just means that the set is prevalent, the set of functions is prevalent if we take for any function, any Lipschitz function, if we add such a perturbation of this form, then for almost all coefficients we will be in this big set. Okay, so once more, we take this vector B, which is here Lipschitz map H. We add some perturbation of this kind, linear perturbation, and for almost all vectors of coefficients, we are in this space, in this set, which we would like to call prevalent. So almost all perturbation, Lipschitz perturbation and all this kind are within. Okay, so this is the definition, and also we'll use it in some more general setup of local Lipschitz map on some Borel set. Then we should play with this norms metric, but the philosophy is left. Okay, so what is the theorem of Sauer, York, and Casvali? So they take not a differential manifold, but a compact set in Rn and a Lipschitz injective map. And the difference here is that in Takens' theorem, we will have only generic map, and here the result is for any dynamics, any given dynamics. Okay, now they take K, which is larger than twice upper box dimension of X. And now if the map is not generic but any map, then we should add some condition for periodic points of low period. Because, for instance, if everything is periodic, is low period, there is no chance that this K delay map will be injective, because everything will return to itself after a small number of times. So we should assume that the set of periodic points of low periods is not too big. So the condition here is that upper box dimension of periodic points of minimal period P is smaller than half P. 4 periods up to K minus 1. And then the assertion is that for a prevalent set of Lipschitz observable, this K delay coordinate maps is injected. And this prevalent set is with the probe set, which consists of polynomials, a linear basis of space of polynomials. So very regular. Okay. So this is also a classic result from the 90s. And I would like to present you a picture from Scholarpedia. There's an article by Sauer, which is called Attractor Reconstruction. And he presents the following picture, which is very synthetic. So this is a Lorentz attractor. It is a subset of three-dimensional space. And we take a point. We do the dynamics. Well, dynamics is continuous, but we can discretize it. And we just measure the first coordinate, x of t. Okay, so this is the graph of x of t. Okay, and now we take three measurements. Some time t, small t is fixed, and there are three time delay measurements. Time t minus capital T, and t minus 2 capital T. So here this is a conflict of notation. Anyway, this corresponds here to three time delay measurement. Well, and he claims that if we draw this three time delay measurement, then it will give an exact copy of the Lorentz attractor. So it is very interesting. But if we read carefully this Sauer-York-Kasdali theorem, then the condition is what? The k number of delayed measurements needed for the embedding should be larger than 2 times upper box dimension of the space. So here it is known that Hausdorff dimension of the Lorentz attractor is 2 plus some small number, 0.6 approximately. So the box dimension is at least 2.06. So 2 if you multiply by 2 and take a minimal integer not smaller than this, we get 5. So this year we need 5 time delay measurements. So this picture in this Colopedia is a bit misleading. Yes.
What is the function h?
The function h here is just the first coordinate.
What I don't understand. Usually, with Lorentz, you have direction. Because if you have a section, standard section, then you have only 2 coordinates, x and y. You have first pair, and virtually often you have stable manifolds, just in the direction of y. So x does not, and even x non trajectory, you should not distinguish these points because they are in common stable direction, so they become close. So maybe x is not the right one. You need some other direction which distinguishes also points in stable.
That I don't know, but generally, well, the point travel around the whole attractor.
Yes,
so,
but points in the same stable, they go on this table all the time together and become very close to each other. The only answer would be if stable is not precisely along y, maybe that's also something.
of course.
Only there is another mistake, because this is one object. What you are saying here is a measurement on one object, one x.
No, because I mean not one orbit from the flow, but stable. Stable is not the orbit. Stable is.
I know. So the point is what you are saying here is take a point and follow its dynamics.
Yes.
That's all.
No, yes. So 2 points have the same orbit.
What you mean? You mean 2 different orbits?
2 different orbits in the same stable.
I understand. Irrelevant, because here it's one orbit.
So yeah, it is not completely clear what is written here. Yeah.
Time is so long that we have time.
Exactly. So this is again misleading.
Anyway, okay. So anyway, here, well, the picture suggests that, well, the 3 measurements are enough.
For one orbit.
Yeah. Oh. Okay, so now the idea here is to work in a probabilistic set. So suppose, and it's quite natural for application, that we have some information not for all the system or space, but almost all. We have some probability distribution. And maybe this will help this general hope. And in fact, there was a paper by Schroer, Sauer, Ott, and York in 1998. In this paper, they generally conjectured that for some good measure, they were considered natural measure, more or less physical measure on the attractor. If we are interested in typical behavior, so we can neglect 0 measure set, then well, generally to get some reliable information of the system, it should be sufficient to consider as many measurement as a dimension, not twice the dimension, but just dimension. This is a very interesting paper. Well, in fact, we found this paper after writing our result. But anyway, this was a very good intuition. In fact, they checked they were made some checking for Henon attractor, and I don't remember which one, the second one. Okay, so our result is the following. So generally, it is called probabilistic Takens delay-embedding theorem, but generally we just consider a Borel, finite Borel measure, or even sigma finite Borel measure. So we have a Borel set in the Euclidean space, a finite or sigma finite Borel measure, and Lipschitz or locally Lipschitz injective map. And we take K such that it is larger, just the Hausdorff dimension of X. So without 2, and Hausdorff is one of the smallest dimensions. Okay, we have also this condition on the dimension of periodic points. Now it is weaker because we do not divide by 2. P is this period, minimal period. So the points of minimal period P has dimensions smaller than P. It is just like in the previous paper, but they took P over 2 because. Okay, and then the K delay coordinate map is injected, maybe not on the whole space, but on some Borel set of full measure mu. And it holds for a prevalent Lipschitz observable, Lipschitz or locally Lipschitz, this K delay coordinate map is injected, almost injected. Okay, and generally we don't assume that the mu has anything in common with dynamics, but if the measure mu is invariant, then this set where this delay coordinate map is injective can be chosen to be invariant also. So this will also embed the whole dynamical system into Euclidean space up to zero measures. Okay, there are some remarks. The first remark is that we can slightly weaken the assumption that K is larger than Hausdorff dimension. It's enough to assume that K Hausdorff measure is zero. But on the other hand, we cannot weaken this condition to equality of K and dimension of X. And the example is quite simple. So take just a circle and Lebesgue measure. So mu is Lebesgue, X is circle. And suppose we have some map into R. So dimension of X is 1 and take K 1, okay, equal. So I claim that any Lipschitz map from the circle to R cannot be injective on a set of full Lebesgue measure. And the proof is very simple. So we take the image of this circle. This is an interval. We choose say the point, minimal point and maximal point. So we know that here there is a point which goes here, and well, somewhere else is the point which goes here. So, well, generally, say this part is mapped onto this interval, but also this part is mapped onto this interval. And suppose this map is injective on a full Lebesgue measure set subset. So then there is this zero measure set which is not good, but the zero measure set is mapped by H, since it is Lipschitz, by zero measure set here. So this bad set in this blue part is mapped onto a zero Lebesgue measure subset here, and also this orange bad set is mapped onto zero Lebesgue measure set here. So there are plenty of points which are outside this image of bad set. Okay.
This is something key because I'm thinking all the time what happens if we have plenty of systems. How to find H.
So suppose we have a Lipschitz map from the circle to R. I claim that this map is not injective, cannot be injective on a full Lebesgue measure set in the circle. So suppose it is. So this is this good. So this suppose H is injective on some set XH, which has a full Lebesgue measure. Okay, so the image of H. So I take the image of the whole circle, take say minimum and maximum here, and some pre-images. Okay, so this part is mapped onto, and this part is mapped also onto. So the image of S1 minus X here in the blue one is mapped onto zero Lebesgue measure set because map is Lipschitz and makes zero set to zero set. and the same on this orange part, which means that here on the full Lebesgue measure subset of this, the points are not in the image of this bad set here and bad set here, which means that they are images of good set here and good set here. But this is a contradiction because the match should be one-to-one on this. Okay, so this is a nice example, and we would like to have it also in high dimension, but so far we are not completely sure how to do it. So yeah, so the question is, yeah, we have a Lipschitz map, say on the d-dimensional sphere into RD. Can it be one-to-one on a full Lebesgue measurement? Okay. Anyway, in general, we cannot have equality. Okay. And a useful thing is that this condition of about the dimension of periodic points, which is not very nice to check, can be omitted in many cases. For instance, if mu is invariant and ergodic, then the measure of periodic points is 0 because the map is ergodic. And if the measure of this point is 0, we can just this assumption, because 0 measure set are okay for us. Yeah? They don't count. Okay, we have also an extension for Holder observables. If we have Holder maps, then the dimension should by this we should multiply appropriately by the Holder exponent. So it's like that. Okay, maybe the reds are not so interesting. Good. So again, and in the language of an experimentalist, we can say that a Lipschitz injective dynamics on a d-dimensional phase space can be almost reconstructed by k time delay measurements of a prevalent observable for any k greater than the dimension of the phase space. So it gives a reduction of twice by weight 2 of this minimal embedding dimensions. So we hope that this could be interesting also for people doing application, because generally this notion of minimal embedding dimension is quite known in the literature, and there are some algorithms to estimate this minimal embedding dimension, which of course generally we know that it is at most 2d+1 by Takens theorem, but in many cases can be smaller. So maybe this can be of interest. Okay, so returning to this Lorentz attractor, now we can see that our condition that k should be strictly larger than the Hausdorff dimension. So three measurement will be enough. So at least these 3 dimensions here are good for almost reconstruction. Yes. So here we can take some physical measures. Okay. So this was the part about dynamics. Maybe you have some questions or comments. If not, now I will tell something about non-dynamical versions of the theorem. Because it appeared that we also have an analog of this embedding theorem for perturbation of one map, not only dynamics. Okay, so the history here is there is a paper by Manier from 1981 with the following theorem. So if we have a compact set in the Euclidean space and take K larger than twice the upper box dimension, or it is also enough to say that K is larger than the Hausdorff dimension of the arithmetic difference, or I think also, okay. And then if we take almost every typical linear transformation from Rn, that is the space where X is contained, into Rk, then it is injected. Here, this almost every means just the Lebesgue almost every, because the space of linear transformation of the Euclidean space is finitely dimensional. So we can take we can take some Lebesgue measure on the space of parameters. Okay. In fact, Manier formulated in not a completely correct way, because he said here that he could take twice Hausdorff dimension, but then he realized that this was not correct, and in fact it is related to some example of Kahn 10 years later, which show that there is a compact set with minimal Hausdorff dimension, just zero Hausdorff dimension, such that any linear map from Rn to Rn minus 1 is not injected on this. Okay, and this is related to the fact that the Hausdorff dimension of the Cartesian product of two sets can be much larger than the sum of Hausdorff dimension of the sets themselves. And it is not for box dimension, and that's why the box dimension is okay. Good. And a few years ago, there was a paper by Alberti, Bolcskei, Lellis, Koliander, and Riegler about probability version of this. So this is maybe I will comment that this seems to be very classical, and in fact, Manier in his paper wrote that he was sure that that many people had proved it before, but he tried to find the proof and did not succeed. But it seems that it is the first written observation. Okay, so here they made a probability version. So we have a Borel set and probability Borel measure, and the condition, like in the dynamical Takens theorem, the condition can be then reduced by 2. So we take K larger than, and here they did something which is called lower modified box dimension. The definition is here, and it is something between Hausdorff and box dimension. The definition is that we take any countable cover by compact sets, we take supremum of lower box dimension of this compact set and then infimum of this coverings. Okay, and then
Similar to the packing, but not.
yeah, this is a variant.
Lower box from the upper box.
And then Lebesgue, almost every linear transformation to RK is injective, but maybe not on the whole set, but on a subset of full measure. Okay, so our theorem also has a version of a non-dynamical version, and we managed to improve a bit this result. So our theorem is that the setup is similar. Well, the measure can be sigma finite, but this is not very important. But we managed to change this modified box dimension just to Hausdorff dimension. So we take k larger than Hausdorff dimension and locally Lipschitz map, and then every linear map L, if we add, if you take such a linear perturbation of this initial map phi, then it is injected on the set of full mesh mu. In particular, if we take phi to be in identity, when we got this extension of this previous theorem, because then there is just map L. Typical map L is injected. Yes, and we have an example. In fact, Adam has produced a beautiful example of a set for which this modified lower box dimension is strictly larger than Hausdorff dimension. Surprisingly, there was no such an example in the literature. It's not very obvious. Okay. So this is the theorem, and one of the corollary is about projection. So we take this. So maybe I will. We take this initial map phi equal to identity. So we just take linear transformation. So if we take a linear transformation into the space of a smaller dimension, it is more or less like a projection. So just taking projections, we have the following corollary. So we have an X in the Euclidean Borel subset in the Euclidean space, Rn, and with some finite or sigma finite Borel measure, and take k larger than the Hausdorff dimension, and then we take projection to k-dimensional linear spaces, subspaces of Rn. And for the typical linear, such linear subset, the orthogonal projection is injective on almost full on a full measure set subset.
Difference between your and Marstrand.
Yes, so exactly. We will compare it with the Marstrand projection theorem. So Marstrand projection theorem is about dimension. So it says that if the dimension of the space onto which we project is at least equal to the Hausdorff dimension, then for typical projection, the dimension of the image will be the same. Here we say not about the dimension, but that the projection will be injected on a set of full measure. So
You
this
want
is
to do more case effectively.
yes. Yes, but for equal, there is no chance. I think that just this example shows. So the two theorems are a bit orthogonal. It's not orthogonal. But well, maybe not orthogonal, but there is no obvious relation. Okay, and well, to illustrate this, so imagine very simple situation. So we have in R3, take a smooth curve, smooth Jordan curve. So, and take projections, yes. So it can happen, of course, for instance, take a flat circle. It for some special direction, it can be mapped onto a set of onto an interval with many like here with many pinches. Yes, but in general, the number of this intersection in the image is smaller. Yeah? It's and it is fine. Generally for general projection it is finite. So if we take just one-dimensional Lebesgue measure on this curve, then a finite number of intersections is of measure 0, and it is well, and our theorem just illustrated this fact. And also here is the Klein bottle, which is so we take Klein bottle in R4, and we project it into 3-dimensional. It has dimension 2. Say it is smooth. We project it onto 3-dimensional spaces. So if we take some 2-dimensional Lebesgue measure on this Klein bottle, then the measure of intersection for typical projection should be should be 0. Yeah, and indeed here it is a circle, a smooth circle which has dimension 1, so it has 2-dimensional measure 0. Okay. Here are some comments on the inverse map. So it is a natural question. If we have some embedding on some subset, then formally we have some inverse map. But what is the regularity of this inverse map? So in this Manier theorem, it was noticed that for a typical transformation L, this map is not only injective, but has a Holder inverse for some small enough Holder exponent. Also, this was extended by Hunt and Kawashim in the setup of this infinitely of finitely dimensional subset of infinite dimensional Banach space, which are well approximable by finite dimensional linear spaces, like this attractors of Navier-Stokes. So remark is that in our setting, the probabilistic setting, there is no general chance for this Holder inverse in general, because if we take so the argument is the following: if we take a set, there are examples, there are classical examples of topological spaces of dimension D which are not embeddable in R2D. So this is this counterexample to Mangan-Nebeling theorem. The 2D plus 1 is optimal. Okay, so take such a set and take some measure which has full topological support on this set X, and suppose that this injective maps this perturbation of linear perturbation of the Lipschitz map phi had a Holder inverse. If it had the Holder inverse, then this Holder inverse will extend to the whole Euclidean space. Okay, so we will have the inverse map psi, which is defined on the whole Euclidean space, and then take the set Y of point small x in X such that the composition of this maps and its extended inverse is identical. And then this set is a closed set of X because these are continuous maps. These are, well, the condition is the equality of two continuous maps. And it has full measure because we know that this exists for a full measure set. So then this means that it is in fact the whole X, because the topological support of mu is X, and we have closed measure of full measure, closed subset of full measure. This is the whole space. But this would imply that in fact we have embedding on the whole space X, which is by assumption it does not hold. Okay, so maybe in 5 minutes I will say something about the proof, omitting more technical parts. So just recall. So I will say there's something of the proof of the non-dynamical version because it is easier. So this is the theorem to prove. A Borel set with a Borel measure, K is larger than dimension, Hausdorff dimension. We have a Lipschitz map into RK, and then we add some randomly some linear map, and we claim that for such typical perturbation, we obtain a map which is injective on a full mu measure set. Okay, so first there's the lemma, which is a known lemma, for instance, in this Robinson's book. We have, maybe I will write it on the blackboard. Here, capital E is the unit ball in the space of linear transformation from Rn to Rk. So this is a finite dimensional space. We have some parameterization and the unit ball. U is some non-zero vector in Rn, V is some vector in Rk, and delta is some small constant. And the lemma says that the Lebesgue measure of L in E is this unit ball, such that the norm of L of U plus V is smaller than delta, is estimated from above by a constant. Here is delta to K, and here is the norm of U to K. Maybe I will not prove this lemma. Lemma is very proof is very easy standard. Okay. just for one screen. We can look at it, and then I will omit. Okay, so now the proof of the theorem. So what is the idea? The great idea here is to use Fubini theorem, because if you are interested, if we can neglect zero measure set, we can play with integrals, theorems about integrals like Fubini theorem. So formally, we take a set A, which is a subset of the Cartesian product of the space and the space of linear maps, of this linear perturbation. So these are just we can assume that this linear perturbation have bounded norm, just by considering a countable union of both sets. So the set is this bad set. This is the set of X and else, such that there is there is some gluing, so that the map phi L glues the points X with some other point Y, which is different than this. Okay, and so this is the subset of Cartesian products. Now we consider sections. So abstractly, we have this X here and this transformations here. This is the set A. We consider this vertical section indexed by X and horizontal sections indexed by L. Okay, and to prove the theorem, we should prove that for almost all L's, so for almost all horizontal sections, this bad set has measure 0. This is exactly the assertion of the theorem. Okay, but by Fubini theorem, since all here is this is the back measure finite, of course Fubini theorem can be applied. So it is equivalently we can prove that all vertical sections for all vertical sections have Lebesgue measure 0. So this is the trick. And now, well, here is only some technical trick that we can assume not only that y is different than x, but that y is in some definite distance of x. Just considering the countable union of set, we can assume that this distance from x and y is definite. Okay, and this set will be called AXN, such that this distance is larger than 1 over n. Okay, and then the whole proof is here. So we have this set. This is a repetition of the definition of this set. We should prove that it has 0 Lebesgue measure. This is the set of this linear maps such that this perturbation agrees at x and y. Okay, and we know this Kn is the set of y's, and we know that the set of y's is in our phase space, which has 0 K Hausdorff measure. This is the assumption that well, we generally assume that dimension is larger than K, but minimal assumption is that K Hausdorff measure is 0. Okay, so we just cover this set by a countable number of balls such that the sums of the radii of the balls in the power k is small. Okay, and we take L and Y like in the set, and now okay, we know that epsilon is very small and x and y are in some definite distance. So it means that y, okay, y is in some of this ball, and now we just estimate. Just make such estimation. So we take the norm of, well, we just estimate this this object. So it is by definition it is such a sum. Then we know that this perturbation of at x is the same as y, so we can substitute here x by y. Okay, and return, and we use the Lipschitz condition of the map, because it's linear map. It's yes, it is Lipschitz, and we and by observing that this set is by this calculation, the set of L's has the following property that the norm of L on some vector u plus v is smaller than some constant times R I, and now we just use this lemma, taking u, v, and delta as here, and by this lemma exactly we got the Lebesgue measure of the set is estimated by the sum. Here is a constant. Here is also the constant in the denominator, because we by the assumption that this is a definite constant, and we just got this sum, a constant time the sum of Ri to the power k, which by assumption is smaller than x. And this is the end. Well, the dynamical part is done a bit similarly, but we must consider also the dynamics. Maybe I will skip it. And here are some papers related to this. So the theorem. So our theorem, which I have talked about today, is contained in this paper, and now we have another paper, and we are preparing the third paper, and I hope that Yonatan or Adam will tell you something about the further work. Okay, so thank you.
Any questions?
I actually have a question.
Yes.
Krzysztof, could you tell me, please, that the technique you just described in this proof, it resembles the technique that we use in dimension theory, which is called the transversality techniques. Somehow, just the lemma which is on this formula is very much similar to this transversality assumption. Is it just by chance, or is there some reason that?
I think this is a question to Yonatan.
I couldn't hear what he said.
Karol, can you repeat exact?
So my feeling is that the flavor of this proof, which has just been described, is similar to the techniques that we use in dimension theory when we handle fractals of overlapping constructions. And we would like to prove that typically, in spite of the overlaps, it happens what we expect to happen, as if there were no overlaps. And then we use this transversality techniques, and it appears to be
right.
Yeah.
So this is not a question to me.
Yeah. Okay. So I think because I what I understand is that this idea is due to Yonatan. Yes. This using so I think it's independent. Yeah. It's for sure it is independent.
I can
but
say I'm not familiar with the IFS. Right?
Okay.
IFS or
Yeah. IFS with overlaps. Yeah.
So I can say I'm not familiar with that. But
But it is
might be very similar.
Yeah.
okay. Thank you.
This I can cite well-known quotation of Marstrand that half of interesting results in analysis is changing the order of integrals.
Not only the changing of the integrals, but this condition which appears on the blackboard or green board is somehow it resembles the condition which appears in the transversality.
Okay. Yes, this is
In Robinson's book.
Yeah, yeah, for sure it is in this yes, Robinson's books, which is I think it is here. Yes.
Okay.
Okay.
Thank you.
Okay, thank you very much.
All right, so let's thank Krzysztof again.